Hi, this is Dr. Sweeney, and today we're going to start a series of videos on relations. Relations play a major role in discrete mathematics and computer science. A relation is an object that is a more general form of mathematical objects that you probably have a lot of experience with, like functions, linear transformations, and graphs. In order for us to better understand these mathematical concepts and to be able to better understand how programs and computer architecture are put together, understanding relations can be very key. In our work with logic and Boolean algebras, we discussed the rules that are at the heart of mathematics and computer programming. In sets, we talked about the containers for objects and how we categorize and talk about mathematical objects. With relations, we're going to start to discuss how we create connections between members of sets. So we'll begin with the definition. Two sets A and B and a set R, which is a subset of A cross B, so it's a Cartesian product of A and B. We say that A, R, B if and only if A, B belongs to R. Or we could also say that B, R, A if and only if B, A belongs to R. And the reason why I did this is because it's important to recognize that A, B is an ordered pair and A, R, B's order matters. So when we're looking at these relations, I want you to kind of keep that in mind, that we're going to have these conditional statements that we're going to write, and whatever one's going to end up in the hypothesis and whichever one's going to end up in the conclusion is really important. We need to pay attention to that. So to give you an example, let's look at a set of ordered pairs. Let's suppose that we have the set R, which is the ordered set pair, the set of ordered pairs 1, 3, 3, 1, 5, 7, 2, 4. So according to this, we have 1R3, 3R1, 5R7, and 2R4. Notice the first term is going to be the first part before the R. The second one is going to be after the R. In this example, we don't know how the pairs are related. We don't actually have a rule that we've set up for that relation. We just know that they are. You'll see things like this, say for example, in training data sets for machine learning. We know that we have a file and we know we have a descriptor. Those two things are related in some way or another. We're looking for the computer or the machine learning algorithm to create the rule to relate the two. Let's take a look at another example. Suppose that we have A, a set which equals 1, 2, 3, 4, 5, and B, which equals 1, 2, 3, 4, 5. An integer x divides y if there's another integer k such that y equals kx. We might also say that x evenly divides y. Pretty simple idea, really. For example, 20 divides 40 because 40 equals 20 times 2, or 40 divided by 20 is actually giving me a whole number. So let's suppose that we create a relation to describe this division. And suppose we call it D, and D is a subset of A cross B, and A dB if A divides B. What we'll do is we'll actually construct a table in order to show what the different members of this relation are. So for example, I'll have here all of my A's, they're going to be in my rows, and all of my B's are going to be in my columns. So 1 divides 1, that's true, that's a yes, I'm going to make that a 1, just like my Boolean algebras. 1 divides 2, that's also true. 1 divides 3, true as well. 3 divided by 1 is 3, all good. 1 divides 4, yes. 1 divides 5, yes. We go down, and now, does 2 divide 1? No, it does not, so we're going to put in a 0. Does 2 divide 2? Yes, it does. Does 2 divide 4? Yes, it does. And so on and so forth, and we can actually fill in the entirety of this table utilizing that division rule. What we'll do now is we'll actually construct the set D. So D is going to equal the ordered pairs. We'll have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 2, 2, 4, 3, 3, 4, 4, and 5, 5. Notice in our relation, the things that we didn't put in is anywhere we have a 0. So anywhere I have a 0, I'm not actually going to put that into the relation. I'm only going to have the things that are 1s in the relation, only the things that actually make the relation true. So one way we could say this is that AB belongs to R if and only if, and we'll use our double arrows for that, if and only if ARB equals true. A really useful way to think about relations is visually. A visual representation that we can use for representations are called line graphs. So let's suppose that we wanted to graph the relation x. AXB is AB belongs to X if A has access to B. So what we're going to have here is we're going to have a relation between a group of people in the set A and what they have access to in B. You might actually imagine this like in terms of a set of security keys. So let's say, for example, that John has access to email and John has access to the LMS. And we have Nguyen, and we know that Nguyen has access to the email. And we have Tanya, and we say that Tanya has access to the LMS. So what this line graph has done is it allows us to generate the set that we'll call X. And X is going to equal John email, John LMS, Nguyen email, and Tanya LMS. And that defines the relation based upon this graph. A relation can be defined on a single set, A. And if that's the case, then we'll call that set A the domain of the relation R. Notice that it's a little bit different from what we have in functions where we have a domain and a target or a domain and a codomain. In this case, we're imagining that R is a subset of A cross A. So when we have that happen, the line graph for such a relation may look a little bit different. So let's say, for example, I have A, and A is 0, 1, 2, 3, 4, 5, 9. And S is a subset of A cross A. So our domain for S is A cross A. A SB, if and only if A squared equals B. So for example, 3S9 is equal to true, so that's going to be inside of the relation S. Let's imagine the line graph, and in this case, because we only have the one set, we can actually just write the line graph as a single set of points. We don't have to imagine it as A on one side and B on the other. So we have 0, 1, 2, 3, 4, 5, and 9. What we'll do is we'll create arrows that point from our A to our B. So for example, 2 points to 4. But we know that 4 doesn't point to 2. And the reason why is because 2 squared equals 4, but 4 squared doesn't equal 2. In addition to that, we'll get 3 pointing to 9. And so when we generate S is going to equal, it's not going to equal, it's going to have 2, 4 in it, and it's going to have 3, 9, but it won't have 4, 2, and 9, 3. Those won't actually be part of this particular relation. Now here's the thing. We also know that 0 squared equals 0 and 1 squared equals 1. How do we represent these inside of this graph? Well, what we're going to do is we're actually going to create a loop. We're going to have 0 point to itself. And what that's going to look like is it's going to look like this. So that means that this relation 0, S0 is true. So we get 0, 0 as a member of S, and we're also going to get 1, 1 as a member of S as well. And we represent those utilizing these loops. You'll notice that essentially 1 points to itself and 0 is going to point to itself. Just like 2 pointed to 4 and 3 pointed to 9. So this is a different kind of line graph. This is the kind of line graph that you can use if you have a relation that's defined on a single set A. Another really powerful way of expressing relations or displaying relations are as matrices or arrays. What we're going to do here inside of this next part of this video is we're going to talk about how it is that we transform a relation into an array or a matrix. So what we're going to do is we're going to define, we've got A cross B, and our A in this case will be our first values in the order pair, and our B's in the second value in the order pair. In our matrix, the set A is going to be our rows, and the set B is going to be our columns. So we're going to generate a matrix, and this matrix, we're going to say its dimensions are going to be 3 by 2. It's going to be 3 by 2 because there are 3 members of A, and there are 2 members of B. So for example, I've got John, I've got Nguyen, I've got Tanya, and they represent the 3 rows of our matrix. Then our 2 columns will represent, do they have access to the email? Do they have access to the LMS? And that'll be our 3 by 2. Whenever I express the dimensions of a matrix, and we'll talk about this more in a later video, I want my rows to be the first value, and my columns, my number of columns, to be the second value. Now what I'm going to do is I'm going to use 0 to represent false, and 1 to represent true. Easiest way to probably do this is everywhere we have an element inside of the matrix, we're going to put in a 1. So for example, John has access to email, so we're going to have a 1 at the intersection of John and email. John has access to the LMS, so we're going to have a 1 at the intersection of John and the LMS. Nguyen has access to Nguyen has access to LMS, so we're going to put a 1 there. And Tanya has access to email, so we'll put a 1 there. Since Nguyen does not have access to email, that'll be a 0, that'll be a false. And since Tanya does not have access to the LMS, we're going to put a 0 there, which is going to be false. So our matrix that represents this particular relation, if we were to just show it as a simple matrix, will be 1, 1, 0, 1, 1, 0. And that's our matrix representation. Let's take a look now at another example. This is the example where we had A as B if and only if A squared equals B. And our set is A, which is the values 0, 1, 2, 3, 4, 5, and 9. Notice that there are 7 elements inside of A, and that our A and our B from our ASB actually happen to be coming from the same set from our domain. So consequently, this matrix is going to be 7 by 7. The 7 values in A by the 7 values in A. So what we'll do is we'll actually generate that. It's going to be a large matrix, or a fairly large matrix. Although in computer science terms, it's pretty much nothing. And now we have 0, 1, 2, 3, 4, 5, and 9. In addition, we'll have that across the columns. 0, 1, 2, 3, 4, 5, and 9. And now, if A squared equals B, then what we'll do is we'll put in a 1. Remember, 1 is true, 0 false. 0 squared is 0, that's true. We know that 1 squared is 1. We know that 2 squared is 4. We know that 3 squared is 9. And we have no other elements. Those are the only 4 elements that actually happen to be inside of the set S. So everywhere else, we're going to put a 0. And that actually gives us our matrix. We have the 7 by 7 matrix, and all we have a couple of values in 0, 0, 1, 1, 2, 4, and 3, 9. And that's how we generate matrices. Remember that our A's, the first value, are going to be our rows, and our columns are going to be our B's. A couple key points to remember here for relations, and then we'll be done. If A belongs to A and B belongs to B, the relation ARB is a set of Cartesian pairs such that ARB equals true. That is basically that if A is related to B, we get a true statement for that, then we're going to put AB into the set. R is then going to be a subset of A cross B, or that Cartesian product. A line graph will create a graphical representation of that relation, and then a matrix creates another visualization of the relation. So we can start out with a line graph, we can start out with a matrix, or we can start out with just the relation, those ordered pairs, and that kind of defines the relationship between our big set A, and our big set B. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.